Before we start solving some basic problems, let us first look at a couple of important ideas in set theory. Let's say you have a set A which contains elements 1, 2, 3, 4 and 5, and consider that you have another set B which contains the elements 4, 5, 6, 7 and 8. Then if you consider another set C, which is the union of set A and B, written as A union B, then this set is going to contain elements which are either in A or in B. So mark the word or over here. And usually A union B, when spoken in English, will turn out as A or B. So what are the elements in set A union B? The elements will be 1, 2, 3, 4, 5, 6, 7 and 8. Note that 4 and 5 are common to both sets A and B. But when you construct a union of the two sets, then 4 and 5 will not be repeated. They will be represented only once. So this is one important point that I wanted to tell you. Now let's define another event or another set D, which is A intersection B. Right? Now this set is going to contain elements which are common to the sets A and B, in which case the set A intersection B or D will have the following elements 4 and 5. And usually A intersection B will also be referred in common language as A and B, reflecting the fact that this is a set which contains elements which are present in A and in set B. Alright, so this idea will be useful in one of the problems that we will solve towards the end of this particular video. Okay, so now let's look at a very simple problem. The problem says that if you flip a fair coin twice, how many possible outcomes are there? Okay, so let's say in the first toss, how many possible outcomes are there? Either you can have heads or you can have tails. So meaning there are two possible outcomes in the first toss. Now in the second toss, again how many outcomes will be there? Either there will be a heads or there will be a tails. And that also means that in the second toss also you can have two possible outcomes. Now remember, the first toss and the second toss are independent because each one of them do not affect the outcome in the other. So they are independent, which means that we can apply the multiplication rule of counting. So if you flip a fair coin twice, the number of possible outcomes are 2 multiplied by 2, and that is equal to 4. So for each of the two outcomes in the first toss, you have two outcomes in the second toss. And applying the multiplication rule, you get the total number of outcomes to be 4. Okay, so it helps to visualize how there can be 4 possible outcomes. So let us look at how we can see this actually happening. So you begin by saying that, look, we are going to do the first coin toss, in which case either you can have heads or you can have tails. And for heads in the first toss, when you do the second toss, you could have heads or you could have tails. Similarly, for tails in the second toss, when you do the, for tails in the first toss, when you do the second toss, you can have heads or you can have tails. So how many different kinds of outcomes are possible? All you need to do is count the terminal branches in what is called a tree diagram. Now you can write the possible outcomes by tracing your path from the origin up to the terminus. So the possible outcomes are H in the first toss, H in the second toss, which is H, H. H in the first toss, T in the second toss. Tails in the first toss, heads in the second toss. Tails in the first toss and tails in the second toss. So here are all the 4 possible outcomes. Now, if I ask the question, what is the probability of getting heads as an outcome when you toss a fair coin twice? Okay, let's see how we can do that. Okay, so here we can declare an event A, which is getting heads in the first toss, and again we can define another event B, which is getting heads in the second toss. Now asking probability of HH means the probability of A and B happening, which is also denoted as probability of A comma B. Now this kind of a probability is called joint probability, and we will discuss that sometime in the future. But let us just look at the problem intuitively. So probability of HH means that probability of A happening and B happening. Okay, now this is equal to probability of A times probability of B. Okay, now why is it that we are able to multiply probability of A and probability of B to get the answer to our question? This is possible because A and B are independent events, right? Because the outcome in the first toss is not going to affect the outcome in the second toss, right? So probability of HH means probability of A and B happening is probability of A times probability of B. Okay, and that is equal to half, because in a fair coin probability of A, meaning probability of getting heads in the first toss, is half, and this will be again multiplied by half because probability of B, that is getting heads in the second toss, is also half, and that is equal to 1/4. Okay, if you do so, let's look at it. Let's write it down here. So probability of PHH, meaning probability of getting heads in the first toss and heads in the second toss, is equal to 1/4. That is what we have calculated just now. Now similarly, if you solve the questions for what is the probability of H and T, meaning H in the first toss, T in the second toss, it will turn out that this probability of HT is also equal to 1/4. Probability of TH will also be equal to 1/4, and probability of TT will also be equal to 1/4. Right? If you add up all of these together, you will get a value of 1. That's fair enough, because what you have here is HH, HT, TH and TT are the only possible outcomes when you flip a fair coin twice. And so their respective probabilities when added together should add up to 1. Because this and this all together become the sample space omega. Right? So with that idea, let us now proceed for the next problem. Okay, so the next problem is a modification of the previous problem. In the previous problem, we considered a fair coin, right? But here we are going to consider an unfair coin. How is this coin unfair? It is unfair because the probability of getting heads in this coin is, let's say, 0.8, which means that the probability of tails is going to be 0.2. It has to be, because heads and tails are the only outcomes when you flip a coin, and both the probabilities should add up to 1. Now, simple things first. Now, if you take this unfair coin and flip it twice, how many different possible outcomes? Well, the number of possible outcomes will remain the same, because for every 2 outcomes in the first toss, you are going to have 2 outcomes in the second toss, and therefore the total outcomes will be 4. And the tree diagram will be essentially the same as you have drawn in the previous problem. So let's write down these outcomes. So first outcome is HH, one of the outcomes is HT, the other one is TH, and the other one is TT. Now, for this unfair coin, let us calculate the probability of HH. So that will be probability of heads in the first toss times the probability of heads in the second toss. Okay, this coin could be unfair, but nonetheless, the first and the second tosses are independent. So I can actually multiply the probabilities. So probability of heads in the first toss is 0.8, and that of the second toss is also 0.8, and both multiplied together give me a value of 0.64 and 0.64. Similarly, let's calculate the probability that the outcome is HT. So here again, probability of heads in the first toss 0.8 times probability of tails in the second toss 0.2. Remember, it's an unfair coin, probability of tails is 0.2, and that will be equal to 0.16. Probability of getting T and H, meaning T in the first toss and H in the second toss, will be 0.2 times 0.8. That will again be equal to 0.16. And finally, the probability of TT equal to 0.2 times 0.2, and that is equal to 0.04. Fine. This constitutes the sample space omega. So if I add up probabilities of each of these possible outcomes, then it should add up to 1. And that's what you have here. If you add all these probability values, you will find that it's all adding up to 1. Right. So what we have learned is that we have been able to calculate probabilities of some defined events using the example of a fair coin and an unfair coin. Now let us proceed to the real thing that I wanted to discuss, and through which I'm going to try and show you one other interesting property of probability. Okay, so let's make the problem a little more complicated. And the problem that we have stated here is that if you flip a coin 3 times, how many possible outcomes are there? Well, I don't think we need to draw a tree diagram once again, although you may choose to do that. But then we can simply say that for each of the 2 outcomes in the first toss, there are 2 outcomes in the second, and also there are 2 outcomes in the third toss, and so the number of possible outcomes is 8. Alright, so what we will do is we will kind of list out all the possible outcomes, and because that is going to be the basis for the next problem that we are going to solve. So the outcomes are H, 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 all 3 heads. Then we have H, H, T. Then we have H, T, H, H, T, T. Then we have T, H, H, T, H, T, 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 H, and finally T, T, T. Alright, so what we are going to do here is we are going to ask the probability of each of these outcomes when you flip a coin 3 times. But then what we are going to do here is we are going to consider that the coin is unfair such that the probability of getting heads is equal to 2/3, which would imply that probability of getting tails with this coin is 1/3. Fine. So let's calculate this probability. So this one will be 2/3 times 2/3 times 2/3, which is equal to 8/27. The probability of this outcome is going to be 2/3 times 2/3 times 1/3, which is 4/27. Similarly, the probability of this outcome, again there are 2 heads and 1 tail, so it will again be 4/27. Well, the probability of HTT will be 2/3 times 1/3 times 1/3, which is 2/27. This will also be 2/27. Sorry, this is going to be 4/27 because there are 2 heads over there. Probability of this event is going to be 2/27, and probability of this event will also be 2/27, and finally the probability of all tails will be 1/3 times 1/3 times 1/3, which is 1/27. Now, as you can see, if you add up all these probabilities, then you end up getting 1. And that's precisely what should happen. 8 plus 4, 12, 12 plus 4, 16, 16 plus 2, 18, 22, 24, 25, 26, 27. 27 upon 27. So if you add up all these probabilities, then it adds up to 1. Fine. Now here is what the problem statement that I want to make. The question here is, what is the probability that you get all 3 heads or all 3 tails? Okay, what is the probability that you get all 3 heads or all 3 tails? So here again, if you look at it in a way, here basically what you are doing is you are defining an event A such that all 3 are heads, which is defined as getting all 3 are heads, and you're also defining another event B, which is all 3 are tails. And when you are asking what is the probability that if you flip this coin 3 times, you will get all 3 heads or all 3 tails, you are essentially asking the probability P of A union B. I think this is understandable because OR will go hand in hand with the union, right? And that, if you look at it, let's calculate this. Now, which of these outcomes are all 3 heads? It is this outcome. And which of all these outcomes are all 3 tails? It is this one. So therefore, the probability of A or B or A union B will be probability of A plus probability of B. All right. And that will be equal to 8 by 27 plus 1 by 27, and that is equal to 9 over 27, and which is equal to 1/3. Okay, so far so good. All right, so now let us ask another question. And the question that we are asking is here, what is the probability that the first or second, or rather let us do it this way, let us say the first or the third toss is heads, or the third toss is heads. Okay, fine. So the question is, if you flip this unfair coin 3 times, what will be the probability that the first or the third toss is heads? Now let us do one thing. Let us try and answer this question exactly the way we solved the previous question. Okay, so here you say A is an event defined as first toss being heads, and you define another event B, which is defined as third toss being heads. Now, asking the probability that the first or third toss is heads is asking what is the probability of A union B, right? So this is what we have to find out. Okay, now if we are going to compute P of A union B as P of A plus P of B, okay, let us see what is going to happen. Okay, what is P of A? What is A? First toss is heads. What is the probability of first toss being heads? Since it's an unfair coin with a probability of heads being 2/3, the probability of first toss being heads is 2/3. 2/3. What is probability of B? How is B defined? B is defined as the third toss is heads. So in this coin, what is the probability that the third toss is heads? That also is 2/3. So P of A union B is equal to 2/3 plus 2/3, and that is equal to 4 divided by 3. Oh, oops, there's some problem because 4 divided by 3 is greater than 1. Meaning there is some problem somewhere. Now, where is the problem? Okay, why is it that this calculation in the previous problem was fair, but here this calculation becomes unfair? Now let's look at it. Okay, so if you look at our previous calculation, see the probabilities of these outcomes are 8 by 27, 4 by 27 and so on until 1 by 27 for the outcome that all three were tails. So what I've done over here is I have these 27 circles. Okay, now imagine if you were to toss this unfair coin 3 times. Okay, in that case, on 8 of the 27 occasions, you are going to have H, H, H. 4 of these occasions, you are going to have H, H, T. All right. Then again, 4 occasions, you are going to have H, T, H. 2 occasions, you are going to end up having HTT. Then 4 occasions, you are going to have TH followed by H. 2 occasions will be THT. 2 occasions will be TTH, and 1 occasion will be TTT. Alright, so we understand that. So we have these 27, and out of 27, the distributions of HHH, HHT will be as follows. Alright. Now, let's look at what we actually did when we used the calculation P of A union B equals P of A plus P of B. Okay, now what was the event A? Event A is that the first toss is heads. Okay, meaning which of these 27 outcomes will qualify for satisfying the criteria laid down in the event A? So it will be right from this particular circle right up to this one, right up to this point. Okay, so because all these are having first toss as heads. All right, now what is event B here? Event B is getting the third toss to be heads. All right, now let us find out which of these circles are satisfying that criteria. So definitely you have these where again the third toss is heads, not this one. Again you have these 4 circles where the third toss is heads, right? Then you have these 4 circles where the third toss is heads, and finally these 2 where the third toss is heads. All right. So for P of A, let us count how many circles we have considered. All right. So for this, we have considered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? So 18 out of 27. All right. Now for the event B, how many circles have we considered? These 8 plus these 4, okay, which means 12, 13, 14, 15, 16, 17, 18, plus 18 by 27. And that is why we had, which is nothing but 2/3 plus 2/3. Now this is the same thing that we had gotten in the previous calculation, right? But then we also know that there is a problem. Now let me tell you where the problem is. Okay. Now, so when we were considering P of A plus P of B, what happened was that these circles, these 8, okay, and these 4 circles, they happened to be counted twice, isn't it? By doing this calculation, you have taken into account these circles and these circles twice, but then that's not allowed, because in the very beginning, I had told you that when you create a set which is a union of 2 sets, then the union of 2 sets is going to contain elements which are in one set or the other set. The ones which are common cannot be entered or considered twice in that set. And this is the reason why you are getting such a weird result. So meaning that we have to do some sort of a correction for the fact that, look, we have counted these 8 and these 4 actually 2 times. All right. So what should be done here? Since we have taken into consideration these circles and these 4 circles 2 times, you have to subtract them once. All right. So therefore, the actual calculation should be 18 by 27 plus 18 by 27 minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which is 12 by 27. So once you have to subtract it. Okay. Now, let us do the calculation and first find out what the answer is. So that will be 36 by 27 minus 12 by 27. And that turns out to be 24 by 27. And that is the correct answer. Now, what is this essentially? Right. The fact that we are correcting for the fact that we have taken some of these circles twice and we are subtracting it once. What is it that we are actually doing? What we are actually doing here is, the calculation is as follows. We are doing P of A plus P of B, and for the correction we are doing minus probability of A intersection B. Remember what is intersection? Intersection set is the one where the set contains elements which are common to both these sets. See, these circles and these circles are common to both these sets and they need to be subtracted. Okay, so with all this, what is the take-home message? The take-home message is that whenever we calculate the probability of A union B, then the most appropriate calculation is that P of A union B will be equal to P of A plus P of B minus of P of A intersection B. Okay, this is the actual calculation that operates. Okay, but then remember, in the first example, when we were doing the example where we asked the probability of what is the probability that all 3 are ends or all 3 are tails. In that question, we didn't end up with this kind of a problem. Why? Because in that case, the two events A and B were only these 8 and only this one. Okay? So what is the difference between the previous problem and this problem? In the previous problem, the two sets A and B were what is called disjoint, meaning that they had nothing in common, which is why P of A intersection B is actually 0 in that case. Alright? So, P of A union B equals P of A plus P of B minus P of A intersection B, and it can be equal to P of A plus P of B provided that A intersection B is basically a null set. That is to say, when A and B have no elements in common. When you have A intersection B being a null set, we say that A and B are disjoint sets. Okay, the final message that comes out of this video is P of A union B is equal to P of A plus P of B if A intersection B equals a null set, that is A and B are disjoint. And P of A union B is equal to P of A plus P of B minus P of A intersection B if A and B are non-disjoint. Okay, so this we have to take into account. Okay, so whenever it comes to solving problems of probability of A union B, you have to figure out whether A and B are disjoint sets. If they are disjoint, you can apply this, but then if they are non-disjoint sets, you have to apply this formula.